Welcome to another lesson. Over the last few classes, we've learned more about the typical forces acting on a body. And in this lesson, I wanted to build on that and have a look at the typical problems you'd encounter. And I've drawn these out as free body diagrams on my page here. So if you've noticed over the last few lessons, whenever we've been looking at force problems, I've been drawing in these forces on some diagrams to illustrate what's actually going on. And these diagrams are referred to as free body diagrams. And depending on how long we run today, I might split the video up into 2 or more parts. Before we get into it, however, I wanted to give you guys a bit of a framework of how to tackle these problems. So let's get into that first. The first thing I want you guys to do when solving these types of problems is that I want you to read the question 2 or 3 times and draw just a picture of what's going on. Don't worry about putting any values in or any directions or forces or anything like that. Just put down a rough sort of skeleton. And that can literally just be a sketch of a box on a slope, whatever's sort of stated or drawn in the problem itself. After you've gone ahead and done that, put in all the known information and mark anything that is unknown. And try relate everything back to Newton's third laws. They'll help you contextualize what's actually going on. So put in the forces like the external forces that are acting, consider the action and reaction pairs, and consider the directions in which the forces are acting in as well. The frictional coefficients and anything that's already given in the problem. So once you've gone ahead and done that, I'd put in all the unknown variables as well. So I'd just mark it on the diagram as a question mark and allocate a variable to them. So if it's something like, find the normal force, just put an n there equals question mark. So once you've gone ahead and done that, you can then pick a coordinate system based on how you think the objects will actually behave. So if you think something's going to move to the right, I'd make the right as our positive direction. So that's how I typically tend to do it. You can do it other ways as well. It's just something that works for me, and I've noticed that it works for many others as well. And once you've gone ahead and picked a coordinate system, you can go and resolve any of the forces that are on an angle, and then you can go ahead and, based on all the information that you already know, you can solve for the unknowns. So now that we've built a bit of a framework of how to look at these problems, let's actually go ahead and apply them to some questions. Before we go ahead, if you'd like to take a quick screenshot of this analysis procedure, I'd go ahead and do that and just have it on the side for reference. So let's begin with our first problem. And let's say that we're going to find the acceleration of this block, which carries a mass of 30 kilograms and has an external force of 100 newtons pulling on it. And this force is acting at a 60-degree angle to the horizontal. In this case, I've already gone ahead and done the sketch. So we got to ask ourselves, what are all the forces actually acting on this block? Well, we know there's this external pulling force of F that's acting at an angle of 60 degrees. And we know that there's going to be a force of friction as well. So if we go back to our previous lesson on friction, we remember that the frictional force actually acts parallel to the surface and is in the opposite direction to the relative movement. So if the box was to move, we'd expect it to move to the right. And that's because the force being applied is on an angle, but we can resolve it in the x direction. So we'd expect that the block itself would move towards the right relative to the ground, which is stationary. So since the relative motion of the block is towards the right relative to the ground, the frictional force will act in the opposite direction. So we can say that the frictional force will act towards the left. And I'll just draw that in red as FFR. And going back to our friction force formula, we know that F of FR is equal to mu times n, where mu is dependent on either being kinetic or static. We also know that this pulling force of F has to overcome the static friction force for the block to actually accelerate. So we have to determine what this static frictional force actually is. So in this case, let's use mu s to see how much frictional force we have to overcome. So if I plug this into the equation, what I get is F of Fr, which is acting towards the left, and I'll just draw that in real quick, is equal to mu of s, which is 0.3, times the normal force. And this is where we have to find our first unknown, our normal force. But before we go ahead, let's actually set up a coordinate system. I'll do that in a different color. Let's say that I'm gonna pick y up as positive, and because I think this block's gonna move towards the right, I'll make x positive in the right direction. And the other thing that's missing on this diagram is the force of gravity that's acting on the block. So I'll go ahead and put that in as well, in blue. So let's go. Now the other forces that are acting on this block are the normal force and the weight force. So what I'm going to do is I'm going to take this block and I'm going to expand it out a little just so it's a bit easier to see. So we have the block itself with a weight force, which I'll put in as blue, and we'll call that the weight of the block is equal to mg. We've got the external force that we're pulling with, which is acting at an angle of 60 degrees, and that's at 100 newtons. In fact, I'm actually going to pull a quick cheeky here, and I'm going to make that 200 newtons. So we'll just make that 200 newtons. And we've got a normal force that's being imposed by the ground pushing up on the block itself. Call that normal force. And we've got the force of friction acting in the opposite direction of what we think the block's going to move in. And that's our static friction. So if we look at the forces in the y direction and we look at the block in the y direction, we know that the block's not actually moving or accelerating in that y direction. So what we can say is that the sum of all the forces in the y direction, where up is positive, is equal to mass times the acceleration in the y direction. You know that acceleration is going to be 0, so we can say the sum of all the forces are going to be 0. And we can substitute all the forces in the y direction. So we've got normal, which is going to be positive because we've taken positive up as positive rather. We're going to minus the weight force, which is mg. And if we have a look at the components of the pulling force, we have an x component here, which we'll call f of x, and we have a y component here called f of y. So we'll just put plus f of y, and that'll be equal to 0. We know that fy is just going to be 200 sine 60. We know the weight of the block is 30 kilograms. So I'll put that in. And we know gravity is going to be 9.81. So we know all these values, and then we can go ahead and find n. So let me take everything to the other side. So n is equal to mg minus fy. And fy is 200 times sine 60, which is just root 3 on 2. So we're going to have a force of 100 root 3 newtons. And I'll go ahead and put that in the equation. So we have the weight force, 30 times 9.81, minus 100 root 3. And if we go ahead and plug these into our calculator, we should get a normal force of 121.1 newtons. And now that we've gone ahead and found out what our normal force is, we can put that in the equation for friction. And the friction will be F of Fr is equal to 0.3 times 121.1 newtons. And remember, this is the force that we need to overcome for the block to actually move. So I'll put that into the calculator and we get a value of 36.4 newtons to the left. So now that we've determined the force of static friction, we need to check that the force that we're applying will be greater than the static friction. So in order to do that, we need to determine the horizontal component of this pulling force, which we've labeled on our diagram as Fx. Now Fx, with just a bit of simple trig, is equal to 200 newtons times cosine of 60. And if I plug that into the calculator, that is 100 newtons. So we know Fx is going to be greater than Fr. I'll just write that down. So we know that the box will experience some movement. Apologies, that should be F of Fr. And we know that an unbalanced force causes an acceleration in an object. So let's look at what's happening in the x direction. We know from Newton's third law that F equals ma. So F of x, where the right is positive, is equal to the m, the mass of the object, times the acceleration in the x direction. We know that the forces acting in the x direction are the horizontal component of the pulling force minus the frictional force. But because we've overcome the static friction, we actually use the kinetic friction coefficient. And I can write that down in the equation as Fx, because it's positive, minus Fr, but we'll put another k there to signify kinetic friction is at work here. And that'll be equal to the mass times the acceleration in the x direction. And this is what we're actually trying to find. F of Frk is going to be equal to the kinetic friction coefficient times the normal force. And if we look above, the kinetic friction coefficient was 0.2. So I'll put that in. And we know that the normal force from before is 121.1 newtons. So the kinetic friction will be equal to 24.22 newtons. And we know Fx is equal to 100 newtons. So we can go ahead and plug that back into this equation. So we can say 100 newtons minus 24.22 newtons is equal to the mass, and we know the mass to be 30 kilograms, times the acceleration in the x direction. So I can take that 30 to the other side, and we can go 100 minus 24.22 divided by 30 will be equal to the acceleration in the x direction. So if I plug these values into the calculator, I should get an acceleration of 2.53, and I've just rounded it up here, meters per second squared. Now, just as a side note, I'd like you to pause the video or at any point, just after the video even, and do the same sort of an analysis, but in that case, I'd like you to make the pulling force 100 newtons and see what outcome you get. So let's go ahead and move on to the next question. Let's say there's a chandelier hanging from the ceiling, and let's say it's supported by two cables that are installed at different angles. And let's say these cables connect to a point over here, which is another string that holds on to the chandelier. How would we go about finding the tension in all these cables? Well, let's take a close look at what's actually happening here. When we look at the chandelier, we have a weight force that's acting on it, which we'll draw in as W as the weight force. And we have a single cable that's supporting its weight right above it. And we'll call this some tension, we'll call it T1. And if we look at it, there's no other forces acting on the chandelier. So we can go ahead and put in our coordinate system. I'm just going to treat up as positive. There's no actual movement happening here, so the acceleration is going to be 0. And we don't really need an x coordinate system, but I'll leave it in there anyway. So if there's no acceleration happening in the y direction, we can just say the forces in the y direction, where I've just made up as positive, is equal to ma of y. And we know this is going to be 0 because there's no acceleration happening in the y direction. So we go, all the sum of the forces in the y direction is equal to 0. And by that logic, we can say T1 minus the weight force is equal to 0 as well. And then I can just go ahead and sub in the values. So we know our weight force is just equal to mg. So I can take W to the other side. It's going to be equal to mg, which is equal to 20 kilograms times 9.81. And we can go ahead and put that in our trusty calculator to give us 196.2 newtons. So what we find is that this cable, which is cable 1, is being pulled apart. So that if I stand at this joint over here, the cable is actually being stretched away from me due to the weight of the chandelier. So if I consider the force of cable 1 from the joint, that force will be acting downwards. And because we know that the system is in equilibrium, these two cables, which we'll call as 2 and 3, will have a component of force in the y direction which will act against T1. So I can go ahead and draw 3 and 2 in tension as well. So I'll mark that as T3 and that one as T2. We also know the angles on these, which are 30 degrees and 60 degrees here. So we can go ahead and take the force equilibrium in the y direction. So let's break these up into their constituents. So we have T2y, and we have over here T3y. And I'll go ahead and put in a coordinate system as well, where y will be positive in the up direction, and I'll put in x as well. So we can resolve these components in the y direction, but I'll just write out all the equations, all the expressions first rather. So we've got the sum of all the forces in the y direction, where up is positive, is equal to m times ay, and obviously we're in equilibrium, so I'll take out ay, that's 0, which means the sum of the forces in the y direction is 0. So we can say T2y plus T3y minus T1 is equal to 0. Now we already know T1, so we can go ahead and plug that in. So we go T2y plus T3y is equal to T1. And we know that the resolutes of T2 and T3 in the y direction are going to be T2 sine 60 plus T3 sine 30 to give us 196.2. We know the value of sine 60 is root 3 on 2 from trigonometry, so I'll put that in, root 3 2 T2 plus sine 30, which is a half, so it's just going to be half of T3 is equal to 196.2. Now we'll notice that we've got two unknowns here. So we need another equation to define the relationship between T2 and T3. And because we know that the system's in equilibrium, we can do this same process, but we can say the forces in the x direction are also equal to 0. So let's go ahead and do that. Let's say the forces in the x direction, where right is positive, is equal to 0. So let's look at the resolutes of T2 in the x direction. So we'll have, and I'll label that as T2x, and I'll label the x resolute of T3 as T3x. So I can go ahead and say T3x minus T2x, because it's acting in the left direction, is equal to 0. And we can go ahead and equate those terms. So T3x is equal to T2x. And we can go ahead and put the resolutes as well. So we can say T2 of cos. Let's just go up and find our angle real quick. Cos 60 is equal to T3 cos 30. Now cos 30 is root 3 on 2 from trig, so I'll plug that in. So root 3 on 2 T3, and cos 60 is a half, so I'll go half T2. And I can go ahead and sub that back into the first equation that we derived up here. So we can rewrite that equation. I'll do it over here. So root 3 2 T2 plus half T3 is equal to 196.2. And we can establish a relationship between these two. Take 2 to the other side, so we can say root 3 T3 is equal to T2. So I'll sub that back into the equation that we got earlier, this one here. So let's sub in root 3 into the equation. So we'll get root 3 on 2 times root 3 T3. And we'll leave this one as is, so it'll just be half T3 equals 196.2. And the square root times square root becomes a whole number, so we've got 3 on 2 T3 plus half T3 is equal to 196.2, which gives us 2 T3 is equal to 196.2. Take that to the other side, so we'll divide that by 2, and we get a force of 98.1 newtons. Now that I know the value of T3, I can go ahead and put that back into this equation here, such that T2 is equal to square root of 3 times T3, which we found above here, which is root 3 times 98.1, to give us 169.91 newtons. And if we think about this intuitively, it actually makes quite a bit of sense, because we see that T2 here is actually working at a greater angle than T3, which means it's taking most of the weight force that's imposed by this chandelier. Which brings us to the end of this question. Let's tackle one more before the end of this lesson, and I think I'll go ahead and split it up into 2 separate videos. Alright, so let's move on to our final question for this video, in which we've got 2 blocks that are in contact with each other, and they're being acted upon by a force of 90 newtons towards the right. And all our other variables, such as our masses and our frictional coefficients, have also been given. And we're meant to find out the acceleration as well as the contact force between the 2 blocks. So let's go ahead and actually draw more of a diagram and see all the forces that are acting on the block. So we got block M1, which is over here, and we got block 2, which is over here, M2, We know that in the y direction, the only forces we'll have are the weight force for each block, so I'll go ahead and draw that in. We got the weight of 1, which is equal to m1 times g, and block 2 will just be w2, which will be m2 times gravity. And we'll also have a normal force because we'll have the surface pushing onto the blocks themselves. And I'll go ahead and draw those in as well. So I'll have N1 to represent the normal force between mass 1 and the ground. And we'll have N2 to do the same for mass 2. In the x direction, we have the external 90 Newton force that we're applying towards the right. So I'll go ahead and plug that in. Now, one of the key things to note here is that we've actually been given a coefficient of static friction. So we need to figure out if this 90 newtons here acting on the blocks would be sufficient to overcome the overall static frictional force in the first place. So let me go ahead and draw in the frictional forces as well, which I'll put in, let's go with blue. So we'll put in Fs1 to represent the static friction between M1 and the ground, and Fs2 to do the same for mass 2. Then we can go ahead and work out the friction on both of these blocks by using the frictional force equation, which we all remember is mu s times n is equal to Fs. And I've just put s there to signify static friction. So let's do it for block 1. We know Fs1 will be equal to mu of s times the normal force of 1. And we know the normal force of 1 is just going to be equal to m1g rather. And that's because there's no actual acceleration occurring in the y direction. So I'll actually also put in a coordinate system. So y is up, where up is positive, and x is positive towards the right. And I've just made that right as positive because if the blocks were to move, they'd probably move towards the right because your force is towards the right. So let's go ahead and put in the values. We know mu s is 0.15. We know m1 is equal to 20 kilograms. And we know g is 9.81. So I can go ahead and put those values in my calculator. And that gives me a static friction of 29.4 newtons. Let's go ahead and do the same for the second block. So Fs2 is equal to mu s times n2. And n2 is just m2 times g. So I can plug that in. 15 times 10 times 9.81 to give us 14.7 newtons. So the total frictional force, I'll call that FTS, is equal to Fs1 plus Fs2, which is 29.4 plus 14.7 to give us 44.15 newtons. And because we have a 90 Newton force acting towards the right and we have this acting towards the left, we know that the 90 Newton force will be greater than our total static frictional force. So we can go ahead and say that this will actually experience some sort of an acceleration. This entire system will experience some sort of an acceleration because there's an unbalance of forces in the x direction. And also because we know there's going to be an unbalance of forces, and so that means there will be an acceleration, and we can go ahead and use the coefficient of kinetic friction when we go about calculating the acceleration. So I'll take out Fs1 and change that to Fk1, and I'll take Fs2 and change it out to Fk2, because we know that kinetic friction is going to be used now and not static friction. And I'll go ahead and plug that back into our equation. So Fk1 is equal to U of k times n1. So that'll be 0.1 times 20 times 9.81. And we'll do the same thing for Fk2, which is going to be 0.1 times 10 times 9.81, and that gives us 19.62 newtons for FK1, and we get 9.81 newtons for FK2. And then we can go ahead and use F equals ma to calculate the acceleration of the blocks, and obviously they'll be accelerating at the same rate. It's not like M2 will be going quicker than M1. So we'll go sum of all the forces where the right is positive in the x direction is equal to mass times acceleration in the x direction. Now the masses are just going to be m1 plus m2, so I'll put that in algebra for now. So m1 plus m2 times the acceleration in the x direction. So I get rid of that. And the forces in the x direction are the 90 newtons minus Fk1 minus Fk2. And then I can isolate Ax and manipulate it so that I can put everything else on the other side. So minus Fk1 minus Fk2 divided by m1 plus m2. And I can put in all the values that we found above. So it's 90 minus Fk1, which we found is 19.62, minus 9.81, which is Fk2. We know the mass of 1 is 10 kilograms. Apologies, it's actually 20. I had it right in the first instance. So 20 plus m2, which is 10 kilograms. And if we put that in the calculator, we get the acceleration, which is 2.02 meters per second squared. And that'll be to the right because the direction of the external force is towards the right. So I'll just write the direction down as well. So now that we've answered the first part of the problem, let's go ahead and work out the contact force between M1 and M2. And I'll just get rid of some of this stuff on the right here, so I can leave the diagram there and do the calculations right next to it. So if we look at these blocks in isolation, let's consider what forces are actually acting on each of these blocks. So we've got M1, which has a 90 Newton force acting on it, this side. We know there's a frictional force acting opposite the direction of motion, so we got Fk1, sorry. We know that there's a normal force as well pushing up from the surface, and we label that as N1. And we know that because M1 is pushing on M2, it must mean that M2 is pushing back on M1. So I can draw that in as well as another force, as M2 exerting force on M1. And this here will be our contact force between the two blocks. So using the same procedure as before, let's look at all the forces that are occurring in the x direction. And I'll put in a coordinate system, but just in the x direction. And we'll make the right as positive. So we can say the sum of all the forces in the x direction, where right is positive, is equal to ma. And because we're looking at mass number 1, so we can say that x is actually x1 and that a is actually ax1. And we can go ahead and substitute all our forces in. So we've got the 90 newtons minus this contact force, which is m21, minus Fk1, which is the kinetic friction, is equal to ma(x1). And we know ax1 is just going to be the acceleration for the entire system, because m1 and m2 accelerate at the same rate. So I can rearrange this equation for m21, so I can go ahead and say 90 minus Fk1 is equal to max1 plus m21. And I can take this to the other, I can take this expression to the other side to give us m21 is equal to 90 minus Fk1 minus MAX1. And this M is just M1. Sorry, I should have put that in before. I'll just get rid of this dot here. So I can go ahead and substitute all my values in. So M21 is equal to 90 minus FK1, which was 19.62, minus M1, which we know is 10, and we know AX1 is 2.02, so I can sub that in as well. And that gives us a contact force, which is 50 newtons, 50.18 newtons between these two blocks. And that brings us to the close of today's lesson. We'll go ahead and do a few more, the remaining, I guess, questions from the previous slides. And I hope it helped. I hope you took something away from it. And as always, I'll catch you in the next one.